So we're going on to our last speaker, Carlos Ortiz, and he's from the University of Puerto Rico at Mayagüez. I'm sorry, I probably butchered that. And he's he's in his third year of undergrad. So Carlos, if you're ready, go ahead.
All right, so thanks for that introduction. So my mentors for this project were Leah Medeiros and Jason Dexter, and the site of this research was done at Princeton University. And so the title of it is Principal Component Analysis, as a tool for characterizing polarized simulated images black holes. And so probably the first thing that stands out of this plot of this slide here is the background image, right? And so as probably some of you know, this is the recent polarimetry results released by the AHD collaboration a couple of months ago. I believe that it was released around May. And so the reason for including this image here is because my project is directly related to these types of images. So the main objective of working with this project is to use PCA to characterize the properties and variability of these types of images in order to use this information to create new image reconstruction algorithms specific for polarization of black holes. So the first thing that we need to know about this is that this polarization can be, generally speaking, described using the linear polarization descriptions of Stokes Q and U. And the reason for that is because this EVPA quantity here depends directly on those two Stokes parameters. The EVPA stands for the electric vector position angle. And as the name suggests, it gives you the direction of the electric vector component coming from the source that we are detecting. And so the EVPA corresponds to the tick marks that we observe in this image over here. And so by studying the patterns of these tick marks, we can find and understand better the properties and structure of the magnetic field surrounding the accretion disk of black holes. So these types of images and this polarization has been described using or studied using what's called GRMHD theory, or which stands for general relativistic magnetohydrodynamics. And so that those simulations can generally be divided in two types, in two main configurations. So the first one that we have in here is what's called SANE model. SANE stands for standard and normal evolution. And so those models tend to have very weak and turbulent magnetic fields in the accretion disk of the black hole. The second type that we have in here are what's called MAD models. And so the MAD model stands for the magnetically arrested disk. And so their configuration usually has very strong and coherent magnetic fields in the accretion disk. Well, in terms of the polarization that both of them produce, SANE tend to produce very disordered polarization in the EVPA maps that we observe in here, in those tick marks, while MAD models tend to produce very organized structures in the polarization that we observe. And so these are the types of images that we want to characterize and that we want to study in order to reconstruct those tick marks that we observe in both of those types of models. So the way that we try to do this was by using something that's called principal component analysis, or PCA for short. And the way that this works is that imagine that our entire images live in a hyperdimensional space, as this one here, where each one of the images represents a vector. Now, what PCA does with that hyperdimensional space is that it creates an eigenbasis that spans the image space. And what I mean by that is that essentially it creates a space where each dimension will explain a certain property of the entire images. So here, these images correspond to what's called the eigenvectors, and those eigenvectors explain properties of the variance of the images. And the way that we use this information in order to reconstruct these types of images is by using a linear combination of those eigenvectors. The eigenvectors are also called the PCA components. And that's important because I'll use that term in the rest of the talk. So by doing this combination of the components, we can approximate a wide range of EVPA maps that we observe in here. And so the idea behind this is to use the minimum amount of those components possible in order to accurately predict these types of images. So one of the first questions that we wanted to answer by this method is to try and figure out the best way of taking the PCA out of polarized images. The reason for this is because, as far as we know, this is the first time that someone is working with PCA out of polarized images. And so it was important to try and figure out that. So the first method that we tried was to take the PCA out of a combined array that contained all of the Stokes, meaning Stokes I, Q, and U. But that one gave really problematic results, mainly because we were combining the total intensity information from the Stokes I with the polarization information coming from the Stokes Q and U. And so we proceeded to perform a second method, which was essentially doing a PCA individually on each one of the Stokes. And that one gave really well results, but it wasn't very efficient in summarizing the polarization information from the Stokes Q and U. And so we end up with the third option, which was essentially combining the linear polarization Stokes in a single PCA. And that one was the most efficient way of summarizing that information. And the reason for that can be explained using this plot over here. But the first thing here is that here what we have are the eigenvalues as a function of the PCA component. And I know that I didn't mention the eigenvalues before, but essentially they are a direct result from each one of the PCA. And so what the eigenvalues tell us you is that they denote the percentage of the total variance that each PCA component explains. And so that's why we're very interested in studying these types of curves here, because they tell us a lot of information about the variability of the overall simulation or images in this case. And so what I want to focus on here is that if we compare the behavior of the curve that resulted from the combination of Stokes Q with the behavior of the rest of the analysis, which corresponds to the individual analysis, basically, you will notice that the behavior is very similar. It's virtually the same one. And very specifically in those first 100 components, you will notice that it is essentially the same behavior. And so with this was evidence to conclude that this method of combining Stokes Q in a single analysis resulted in the most efficient way of dimensionality reduction, because essentially this is explaining us the variance of two properties in a single analysis. And this is due to the fact that both of them explain very similar information. Both of them are used to explain the linear polarization of a source. So we also compare these types of curves between the two types of models that we had. And so I want you to focus on this very first point of each one of the curves, because it turns out that my mentor found in one of her papers that that very first eigenvalue can be used as a measure of the structural variability in the simulation in all of these images. And so here what we are seeing is that since MAD had a higher first eigenvalue than SANE, this means that SANE is more structurally variable than MAD, than the MAD types model. And so it will be much more difficult to reconstruct images using this method for the SANE type models than what we can do for the MAD type models. We also compare these curves between the inclinations, and we found that the inclinations of the black hole do affect the degree of structural variability. So from this plot over here, specifically in this region, and using the same idea as the previous plot of the very first eigenvalue, what we found is that low inclination models tend to be less structurally variable than higher inclination models. Since here the 60 degrees black hole images have very low, has a very low first eigenvalue in comparison to what we observed in the lower inclination here of 25 degrees. And this could be potentially due to the presence of Faraday rotation effects in these images. So here what we have is a summary of the first 20 PCA components of these types of analysis that we did. And so each one of the images represents one of those components. While the percentages on top of each one of them are the eigenvalues for each one of the components. And so here what we observed is that if you focus your attention on each one of the components, you will notice that each one of them encoded a very specific pattern of the EVPA of the overall image. And so with this, by using or combining these components and these patterns, we can approximate a wide range of EVPA maps. And so here we have an example of those reconstructions using the previous idea. And so here, this is the original snapshot, while these are reconstructions for using 20, 40, and 100 PCA components. And so if you compare, it turns out that by using 20 components, we were able to reconstruct most of the general position and direction of the original tick marks that we observed in the original snapshot here. But it also smoothed over some of the small scale details of the original image. For example, in this region over here and in this region here, what we observed is that it tends to depolarize those regions by using those 20 components. But by improving those components and using 40 components, we were able to create more accurate approximations of the original images. And so if you compare these regions with the ones from here, you will notice that they were much more accurate. And if you improve that by using 100 components, this will give a much more accurate reconstruction. And so the idea with this is that we were able to approximate these types of images by only using 20 to 40 components out of 500 components from each one of the analysis that we conducted. And so that is a great dimensionality reduction. And that's why this result in particular, it's very important for EHD data set. So from these results, we demonstrated that a linear combination of just a few PCA components can be used as a potential model to reconstruct EHD data. And so for the following steps of this project is to try and fit this data set to EHD data in order to prove this hypothesis. And thanks for your attention, and that will be all.
I had a question about the first eigenvalue versus PCA component plot that you showed when you were trying to pick out whether or not to combine Q and U.
Here?
Yeah, this one. Yeah. So
okay.
I guess I'm confused on why the combination is better, like based on this plot, why the combination of both is better than individual, like using them individually.
Okay, yeah. So basically here, the black curve is the analysis for the combination of both of the Stokes. The other two curves are for both of them, but individually, right? And so the reason that we mentioned or that we established that based on this plot, the combination of those Stokes was better is because if you observe basically here, these curves, what tells you is that you can explain the same amount of variability or variance, better to say, using the combination of the Stokes Q and U in a single analysis because of the behavior of the curves are very similar in this region over here. Not sure if that answers your question.
So, because I mean, they look like they pretty much overlap with each other. So,
exactly.
I guess, but then like towards the end, the black one's higher, meaning you'd have to include more components for that one. I guess, is it, if you use the two individually, do you have to like use twice as many components? Is that why using them?
Yeah, so basically by using them individually, we will have to use more components, so more variables in order to reconstruct these images.
Okay.
That's okay. the idea behind it, basically.
Gotcha. Okay, thank you.
You're welcome.
Okay, and Andrew, you can go ahead and ask your question, and you'll be the last question for this session.
Okay, thanks, Aaliyah.
Mhm.
Carlos, nice talk. I had a question maybe similar to Kelly's about slide 9, where you were looking at the inclination effects. I was curious, there's such a big difference for the blue curve, the theta equals 25 for the first component compared to everything else. And I was just wondering if there's a way to understand like why the first component behaves in a different way from everything else as a function of inclination.
Well, that's a great question. So because my mentor found, and I think that this is here in this slide over here, right?
Mhm.
So that first eigenvalue can be used as the measure of the structural variability, because it is able to, if you have a first eigenvalue that it's higher, it means that that analysis was able to summarize it was able to summarize more variability of the overall simulation. So the other components have less variance summarized in them. That's why they differ. Not sure if that answered your question.
I think so, because so basically it's the blue curve might be high in the first component, but then it would be low in this next component.
Yes.
Because it would, everything has to add up to 100%.
Yeah. These are normalized, if I'm not mistaken, these eigenvalues. So if you were able to summarize a very big percentage of the total variance in that first eigenvalue, then the rest of the components will have lower percentages in comparison to the rest of the higher inclinations.
Gotcha. Okay, thank you.